Hello friends, in this lecture we will learn about one string matching algorithm that is known as Knuth-Morris-Pratt algorithm, or in short KMP algorithm for string matching. So you are already familiar with string matching, and the beauty of KMP algorithm is that it can match the string in theta of n times, where n is your length of the string, okay, of the pattern of the string. So let's try to see what is this algorithm about. So the problem is quite simple, the string matching problem, as such that you are given a string S and there is a pattern, okay. So you need to find the pattern in that particular string, okay. So for example, this is KMP algo, okay. So if this is there, and if I ask you that find for me is the pattern P is equal to KMP, is it there in this string T, okay, then you are going to search this, okay, and this is our problem which KMP is going to solve very efficiently. So moving further, so the basic approach, the simplest one, is just which is known as shifting the window, okay. So this is our string S and this is the pattern ABAA, which you have to find in this string. So how we will go about it is just this will be the window and we will be kind of sliding this window by 1 till we reach match the complete text, okay. So ABA, so we match like this AB, so these two matches, but then A does not match, so we will shift the window. Now we will do something like ABA, again it doesn't match, so we will move further. So ABAA not matching, so we will come ABAA. So now this window is matching with ABAA, and this is the algorithm, the sliding window kind of naive algorithm. And if we see, so if the text length is n, so length of text is n and length of your pattern is m, then this algorithm will take O of m into n times, okay. But this, if the pattern is long and the text is length is long, this would be taking a long time, okay, and we don't like this one. So next is the Knuth-Morris-Pratt algorithm, okay. So why it's so important, and in fact I got a lot of requests to put a video on this particular algorithm. So the Knuth-Morris-Pratt algorithm, the basic idea is don't do the same thing again and again. That's the simplest idea, okay. Don't do the same thing again and again. If you have done it, so it's something similar to kind of dynamic programming. Don't do the same problem again and again, but try to reuse that thing, okay. And that's what is KMP, and it uses this basic idea very beautifully. So what we have here is, we have for this string matching algorithm, we have a pre-processing. So in this pre-processing, we basically make a vector pi. So this prefix function, so that's called a prefix function. So this is for a pattern, it encapsulates knowledge about how the pattern matches against the shifts of itself, okay. So this we will see with example, but it basically says that the window which we saw, which was moving in the naive algorithm by 1, here we will try to move it by some larger value, so that we can move the window faster and we can check if it is, the pattern is available or not. So that being said, of course everything become much more clearer with some example. So this is the compute prefix function algorithm. We will first take one example and then we will come to this part, okay. So we have here one example, okay. So here we have one example which is ABABACA. So this is the pattern we have to find. Now the thing is, let's try to see the what is the pi vector. So pi vector tells that the value of pi, let's say k, is the length of the longest prefix of p. Okay, so the length of longest prefix of p, that is a proper suffix of the pk. Okay, so I will just write it. So length of longest prefix of p, the length of longest prefix of p, which is a proper suffix of pk, and pk here means the pattern, the substring of pattern from 1 to k. Okay, so p1 to k is pk, and proper suffix means that suffix should be smaller than the string itself. Okay, so this being said, now let's try to see. So what will be pi of, let's say, 5? So pi of 5 means what? So we want to find for the pattern p5, means 1 2 3 4 5. For this pattern, what is the length? So what is the length of the longest prefix of this pattern? Okay, that is also a suffix of this. So let's try to first try with 1. So if we have a 1, so this is a suffix also of this one. Okay, so this is fine, but we will try for a larger value. ab, this prefix is not here. aba is also not there. aba, in fact, it's there. So this aba here is also a suffix of this pattern. ab, so this is not the suffix of this p5. Okay, so this pi of 5, we find it is 3. Okay, and from this calculation also you will see pi of 5, it's not calculated here, but pi of 5 will be 3. So basically pi of 5, length of the longest prefix of this pattern, which is a proper suffix of p5. So p5 is ab, aba, and what happens, pi of 5, so the longest prefix of p, aba, is also the suffix of ab, aba. Okay, so this is there how you compute pi. So now we calculate this pi for pi 1, pi 2, pi 3 till pi of m. Okay, that's what we do. And in fact, if we are doing this, this algorithm should also be very efficient, because otherwise, even to compute this pi, your naive algorithm might require O of m square times, I think. Okay, it might require that much of time if you make a very simple 2 for loop algorithm. Okay, so it should not be like that. If you have to do something better so that it comes in around theta of m time. Okay, so we construct this. So let's try to see first with simple example how we calculate this. So finally, if you see here, so let's try to see. So we have a b a b a c a. Okay, a b a b a c a. This is the pattern. So this is p is equal to this. So what will be pi of 1? Pi of 1 will always be 0. Why? Because you should have a prefix which is not a proper suffix. So this will be pi of 1 is 0. Pi of 2, let's try to see. P of 2 is, so p2 is ab, and what happens, so your length 1 prefix a is not a suffix of p2, and ab is a suffix of ab, but it's not a proper suffix. So pi 2 is 0. Now let's try pi of 3. So pi 3, so your p3 is a b a. So 1 a is a suffix of this, ab is not a suffix of this. So pi of 3 is 1. Pi of 4, so you have p4 here, ab, ab. So now A is not a suffix of this one, AB is a suffix here, ABA, it's not a suffix. So this will be pi 4 will be 2, your pi of 5 ABABA. So P5 is ABABA. A is a suffix of this length 1, AB not a suffix, ABA, so ABA is a suffix of this, ABAB, ABAB is not a suffix. So pi of 5 is 3, pi of 6, let's try to calculate. So pi of 6 ABAB AC. So now you see C is there, so pi 1, so 1A is not a suffix of this, AB is not a suffix of this, ABA, ABA is not a suffix of this, ABAB, so ABAC, so it's not a suffix here. So and ABABA is also not a suffix. So basically this one is 0, pi of 6 is 0, your pi of 7, now you have one more ABABACA, so it will be 1 if you calculate. So this is there. So pi 1 is 0 based on our calculation, pi 2 is 0, pi 3 is 1, pi 4 is 2, pi of 5 is 3, pi 6 is 1, pi 7 is 1. So this is what we calculated, but we will see that we can do something better. So what I was doing, so this will somehow become, I guess it will become O of M square kind of algorithm, but it will be something bigger. So we would try O of M kind of, theta of M kind of algorithm, and that's how you do, that's the beauty here. So you will see how KMP algorithm calculates this such that it can be done in lesser time. So let's see this algorithm.